Okay, so we're going to continue with chapter 4 on proving if-then statements with a direct proof. The first statement we're going to prove today is using the definition of divide. So let A, B, and C be integers. Here's the statement. Prove if A divides B and B divides C, then A divides C. Okay? Okay. So for direct proof, we follow our template. We assume the hypothesis. We know what our conclusion is going to be. We know we're going to conclude with therefore A divides C, and we're going to use the definition of one integer dividing another to help us. Okay? So let's suppose, and oftentimes if you know, to make this statement a little easier, I'm making this assumption that A, B, and C are integers. And oftentimes that's really pretty much all we're going to deal with in this class, either integers or natural numbers. So oftentimes it's clear what A, B, and C are. I mean, we've only talked about integers dividing integers. So you could say, suppose A, B, and C are integers, and A divides B and B divides C. But let's just say, suppose A divides B and B divides C. Okay, so it's clear from the context we're only talking about integers. All right. So the last statement of our proof will look like, therefore, A divides C. Okay? All right. So we're going to, the next step is we're going to unravel these definitions. A divides B. The definition of A divides B means that I can write B as A times some other integer. Right? So then B equals A times some other integer. Well, I've already used A, B, and C in my proof, so an arbitrary integer, let's try, how about M? B equals A times M for some integer M. Okay, I've introduced another letter. I need to define what that letter is. M is an arbitrary integer. Now, B divides C. That means if B divides C, I can write C as an integer multiple of B. So you might say something like, similarly, C equals B times some integer. Say B times N for some integer N. Okay? So I've used the definition of divides twice in the hypothesis. If I went from the back forward, go from the end back to the front, I need to unravel this definition. So give me a next to last sentence for this proof.
Then C equals A times some integer.
Yeah, so we need another letter, right? So C looks like A times some other integer. So what do I use? You say O? I would stay away from O's. Why?
Like
They look like zeros. Yeah, so how about
K?
K? Yeah, let's use K. So how about therefore C equals A times K for some integer K. So basically, this proof kind of writes itself to this point. You know the direct proof technique. You suppose P, and you conclude therefore Q. You unravel the definitions, and look, we've got to be close to the end. There's not much room here. Right?
Substitute A for B.
Yeah, so we need to get a statement, an equation involving the letters C and A. Well, you have C equals B times N, and you have B equals A times M. So you see, by a substitution, if I replace B with A times M, that'll get me looking like this. Okay. So then C equals, so I'm going to have a set of parentheses here. So I'm going to replace the letter B with an equivalent form, A times M. And by writing it this form, by writing parentheses around it, it kind of tells the reader that, hey, they did something here. What's going on here? So let's look at the previous line. Well, it was B times M, and now all of a sudden now there's this parentheses A times M. So it gives the reader a clearer understanding that, okay, you took out the B and you replaced it by AM. Okay? But, you know, essentially you're done. I mean, there's kind of this grouping symbol in the way. I would probably write one more chain of equations. This doesn't really look like A times an integer. It looks like A times AM times an integer. So I would write probably something like that. A times MN, because now it does look like A times an integer. And now, again, this is where, you know, if we were proceeding from the top to the bottom, you might just say equals AK for some integer K, which equals MN.
K is equal to
Yeah.
M times N.
Yeah, so but the way since I wrote this already, then C equals AK for some integer K, but what does K have to be? K stands for K equals MN. Now that's the definition of A dividing C. So therefore A divides C. All right, any questions? So, you're going to help me now with a proof. You guys are kind of already broken up by pairs, so you can work in pairs. So I have a 6-year-old, and he got a hold of my handouts and put them through the shredder. And so I need you guys to help me put my proofs back together. So I'm going to give each group a copy of this proof. You guys put it in order. You work together. If you want to work with another group, you can. Or if you want to take on a challenge for yourself. Yeah.
That would be the one, because that's your actual.
So I'll tell you, this is a direct proof, right? I mean, it was a direct proof. Okay, everybody got the first line correct. Very good.
Yes.
one. That's that. Maybe. Very good. Everybody got the second line. Yeah? Yeah, so we're gonna wait for everybody else. Make sense? You ready? Suspect there might be a couple of variations, because there's kind of different ideas in the proof you might have them in different orders, but.
So we get this, and then we add one piece.
Should we confront the box, top bottom, makes sense, maybe not.
These three have to go together. I think this one.
Did you guys look at your two compare? You get the same thing?
And then this definition
Left side is still really weird. You'd have to add a lot more first. Right. But I can really do it.
Go from a squared to a cubed.
I don't like that. This completely changed. My teacher doesn't want me.
Yeah, I heard that happen. I heard plus and value.
She wasn't there on Friday. Thursday, she had asked me to go to the child.
Yeah.
Okay.
And she didn't want.
This one.
This
This is just saying
And
2 is greater than 1 if A is 1.
I came on Friday
Plus.
and she said,
So, they have, it's either, there's no different parity, it's the same parity, so they're either, same parity means they're both even or both off. Opposite parity, yeah, it's kind of like you can't find parity for one integer, because parity is like, that has like a pair. You have to have two numbers, or you can just have a pair. So, same parity is both even or odd, both odd. The opposite parity, one's even or odd.
These were introduced up here.
Yeah, it might, it's just a, we'll see some examples of some problems where it makes sense easier to say that two numbers of the same parity, then this is more all one five. It's either the same if X and Y are both
But I mean, no one's
Well, yeah,
no
you know.
one is greater than A. Which is our thing. So AQ plus 1 is greater than Yeah, I don't think there's more. Is that the case?
Sure.
We don't like this one.
Well, I wrote the proof, so all the lines are necessary. Okay. Yes. Maybe. Okay. All right. So let's go. So remember, this is a direct proof, right? So you know, I mean, that knowing what a direct proof looks like should have guided you somewhat, right? You know, everybody got the first line, right? I mean, the statement that you're about to prove. The first line of your proof is, for direct proof, looks exactly like this, right? You're assuming the hypothesis that A is an integer, and suppose that A is greater than 1. Okay? Everybody's last line is correct. Therefore, A cubed plus 1 is composite. Right? All right. So then what we do when we wrote our correct proofs, what was the next thing we did?
Line before the.
You use the definitions, right? You unravel the definition. So we're going to unravel. I mean, here, you know, there's no definition to work from. A greater than 1. But there is a definition here we can unravel. Being composite. So maybe you look back at your notes and said, and what does it mean exactly that an integer is composite? Well, it means, our definition is there's a divisor of A cubed plus 1, and not just any divisor. What about that divisor?
It's less than A plus 1.
Yeah, it's got to be, the divisor has to be between 1 and the number itself. So it has to be between 1, 1 is less than some divisor, which is less than A cubed plus 1. So which one of your sentences looks like that?
Thus, A plus 1 is the divisor of A plus, or A cubed plus 1, with 1 less than A plus 1.
Thus, A plus 1 is a divisor. Now, you would not have, and if you're writing this on by yourself, you wouldn't have written that, because, I mean, if you just have this, you don't know what the divisor is. Okay, so the proof going forward, this is your guide. This is your divisor, and the rest of the proof is going to be showing that A plus 1 is a divisor of A cubed plus 1 with 1 less than A plus 1, which is less than A cubed plus 1. So some of you don't like working from the back to the front. I've seen some comments you've made, but this is kind of essential here because you get these two lines, and this kind of tells you what the rest of the proof was about. Yes?
Can we keep these, and can we number them right on?
Yeah, you can keep them. I'll just do it all again next time. It's not that hard. No, it's fine. No, it's my son. Remember, he ran into the shredder, right? Let's get my son to do that again. No, it's fine. Yeah, I'll be able to keep track of these. If I had like 10 little Ziploc bags or something, but yeah, and actually, I'm going to give you a copy of the finished proof, so you can do whatever you want to do. Okay, you can challenge your roommate to organize this proof. Okay, all right. So think about this. So A plus 1 is a divisor of A cubed plus 1, and A is between 1 and A cubed plus 1. So up here, that's kind of, you saw those sentences. I heard some comments about, there was a statement about like A squared. Well, that probably came before the statement about A cubed, and I heard these kind of things, and you kind of had to figure out what's going on. Okay, well, this is the way that somebody would have written this proof is you see these type of integers. And from experience, you notice that this is always composite, like with actual numbers. Like you plug in any integer, like plug in 2, right? Like 2 2 cubed is 8, 8 plus 1. 8 plus 1 is 9. So 9 is composite. And like somehow you just notice this. And so then you write your proof, and somehow from experience you kind of tell what the factor is going to be. Okay, from anybody who's taught college algebra, you'll see these type of expressions. This is actually the sum of cubes. Have you ever seen that special factorization formula for a sum of cubes? Maybe you've seen difference of squares, right? A squared minus b squared. That's the a plus b times a minus b. There's the lesser known factoring formulas are like a cubed plus b cubed and a cubed minus b cubed. This is the sum of cubes and the difference of cubes. So the a cubed plus 1, that's the same as a cubed plus 1 cubed. And so I know there's a special factorization formula. And so it's kind of, this is the way, somebody wouldn't just sit down to prove a theorem like this. And they would know, they'd have experience using these things, and some other experience that you maybe don't remember the sum of cubes formula. Okay? But it is true that you can factor a cubed plus 1, and the a cubed plus b cubed would factor as a plus b times a squared minus ab plus b squared. So that's the factorization formula. If I plug in 1 for b, you get a plus 1 times a squared minus b plus b squared. So in my mind, I'm thinking, I notice, okay, a cubed plus 1, that's the sum of cubes. I know I can factor that. So I would say, note that a cubed plus 1, it factors, right? I mean, think about it. We're trying to show it's composite, so we can show that it factors some way. We need a divisor. I would say this is a plus 1 times a squared minus a plus 1. I said plug in 1 for b, sorry. So it's a squared minus a plus 1. Okay? That's what I would say. So what did you put for your second line?
Since a is greater than 1, we have a plus 1 is greater than 1 plus 1 equals 2 is greater than 1.
Okay. Yeah, since a is greater than 1, then which one? So since a is greater than 1, we have a plus 1 is greater than 1 plus 1, which equals 2, which is greater than 1. So how many other groups did that next? Everybody? So if someone was reading your proof, would they say to themselves, why on earth are they putting this inequality in this paragraph? Do you think about it now? Does it make sense that a plus 1 is greater than 1 plus 1, which equals 2, which is greater than 1? So why would we need to know that a plus 1 is greater than 1? Why do we need to know that a plus 1 is greater than 1? It's here at the end. We're trying to show that a plus 1 is a divisor, but not any divisor, just any divisor. It's a divisor that's greater than 1 and less than a cubed plus 1. So if you have this in mind, that you have a factor, you already have a factor or a divisor of a cubed plus 1. Okay, we have a divisor now. Now, not only do we have a divisor, we want to show that this special divisor satisfies this inequality. So that's why I wouldn't put that a plus 1 is greater than 1. That chain of inequalities next.
Logic I use went from a plus 1, which is power of 1, then we went to the a squared,
right,
and then went to a cubed.
Right. So, but you see what I'm saying? Without writing this, why would you need to know anything about a plus 1? It wouldn't be clear. It wouldn't be clear to me that, okay, you start with a plus 1, you start with a greater than 1. Why would you need an inequality involving a plus 1? This is why. Well, I'm showing you that a plus 1 is a factor. Now that we know that it's a factor, we can show that this thing right here further satisfies this stuff. Okay, so I had a couple questions. Samantha?
I was just going to say, I had that like right down at the bottom, so that.
Okay. Okay. Another question.
So if you have a greater than 1 and you know you need a cubed, could you do the multiplying by a on each side of a greater than 1 first?
Why would you do that though?
Because you want something with a cubed in it.
Well, you want, that's true, but you want to show that a cubed plus 1 is composite. So the definition of being composite is that you have a divisor that's, so, I mean, I guess you could try that, but, so think about this. So if a cubed, we know that a cubed plus 1 factors like this, okay? Now, this is not enough to conclude the end, right? Like if I wrote this and wrote this is not a complete proof. Because I have not shown, I've shown that a plus 1 divides this. I showed that a plus 1 is a divisor, but I have not shown that a plus 1 satisfies this. So that's the idea of this proof that's showing that a plus 1 is composite. I want to get a divisor and then show that that divisor is between 1 and a plus 1. Okay? So let's see. The next statement that I would include in my proof is since a plus 1 and a squared minus a plus 1 are integers, a plus 1 divides a cubed plus 1. Now, wherever you put this statement, maybe this one was after it. Did you guys have this one followed by this one in your proof? Okay. So, what does it mean that a plus 1 divides a cubed plus 1? Well, it means that a cubed plus 1 looks like a plus 1 times an integer. Okay. So maybe you could have gone backwards. But. Okay. Now, all right. So think about my goal, right? I'm trying to show that a cubed plus 1 is composite. I've got a divisor now. That's not enough. I need to show that a plus 1 is between 1 and a cubed plus 1. So the next part of my proof is going to be showing that a plus 1 is greater than 1. And then the next part is going to be a plus 1 is less than a cubed plus 1. Then I can conclude that a plus 1 is a divisor with between 1 and a cubed plus 1, and then I can conclude a cubed plus 1 is composite. Okay, so my next proof, next line I'm going to show that a plus 1 is greater than 1. Okay, since a is greater than 1, we have a plus 1 is greater than, well, if a is greater than 1, then a plus 1 is greater than 1 plus 1. Okay, does that make sense? If this number is greater than 1, then a plus 1 would be greater than 1 plus 1. And 1 plus 1 is clearly greater than 1. Well, I wrote equals 2. Greater than 1. Okay, so that's good. So now I've shown that a plus 1 is a divisor of a cubed plus 1. I've also shown that a plus 1 is greater than 1. Lastly, I need to show that a plus 1 is less than a cubed plus 1. So then the line goes also by multiplying both sides of a greater than 1 by a, we have a squared is greater than a, and therefore a squared is greater than 1, because a is greater than 1. All right, then you do the same trick. So now, multiplying again by a, I'm just going to write it, I'm running out of room here. Multiplying both sides by a again, you probably got those two lines in the right order, right? By multiplying both sides by a, and then by multiplying both sides by a again, so that's probably, you got this one right. So multiplying both sides by a again yields a cubed greater than a. So only one left, bro. So adding 1 to both sides gives a cubed plus 1 is greater than a plus 1, which is the other half of the compound inequality. Okay. So therefore, thus a plus 1 is divisor. That's what I first established. I first established that a plus 1 is divisor of a cubed plus 1 with a plus 1 greater than 1. That's the next thing I established. And a plus 1 less than a cubed plus 1. Therefore, a cubed plus 1 is composite. This deserves a QED. Just a little box. Okay. So when I've done this activity in the past, I see how you gotta have these chunks, right? There's like this chunk on a plus 1 greater than 1. There's this chunk on about a cubed plus 1 greater than a plus 1, and then I've seen this, maybe this comes down at the bottom. But I would argue that this would be the correct order because you're establishing a divisor. Then you're further giving statements that prove that that divisor is both greater than 1 and less than a cubed plus 1. That's what you need to conclude a cubed plus 1 is composite. Okay. So this will not be on the quiz on Wednesday. Okay, so this is the longest proof we've done so far, right? I mean, only in the 2 days we've been doing these direct proofs. So this is, eventually you get to this point. The proof I just did on if A divides B and B divides C, then A divides C, that was a proof that I saw a student give a senior presentation last semester, and that was one of the proofs that she did without any practice. So that was kind of using her definitions of her topic was on number theory and things in number theory. So this is a nice little theorem. But this is too much for us right now, right? But you see the kind of process, okay? How to think logically and how to have different portions of your proof. But the direct proof is a direct proof. Okay. I went a little long, but we still take a couple minute break. Okay, take a couple minute break, and then we'll start talking about proving direct proofs using cases. Okay, let's take 2 minutes.
Yeah.
I think there was someone else's students who that and that one.
Sorry?
So I think there were someone else's students doing that and that one they had all.
Divide.
Yeah, I was using our absolute value and it breaks up into cases and subcases.
Yeah. That's a classic example of proof by case. Like if for absolute values, it depends on if you're talking about positive or negative numbers.
I think it was like the absolute value of A plus B is equal to the absolute value of A plus the absolute value of B.
So here's your homework. These are, again, just direct proofs using the definitions that we've gone over so far. So page 98, number 4, 6, 7, and 11. So the next section in chapter 4, we'll talk about 4.4, writing proofs, direct proofs using cases. Okay. 4.4, using cases. Okay, oftentimes when you have a statement involving integers or natural numbers, you can break down the proof into smaller kind of sub-proofs, and each one of those sub-proofs is just establishes the truth of the statement for each case. Okay. So you kind of sometimes proof by cases is also another name for it is just proof by exhaustion. You get so tired at the end, you're exhausted. No, you exhaust every possible case of the proof. Okay, so proof by cases, or sometimes called proof by exhaustion. Okay, so the idea is, let me try this up. So I'm proving a statement is true. It may be helpful to consider multiple cases Okay, here's an example. Prove if n is a natural number, then n squared plus n plus 3 is odd. Okay. So the statement is very similar to a problem you did for homework, right? It's something similar like, you start out with, I think, an odd integer, right? So if n was odd, then some quadratic in n was also odd. Okay, so if you have, you know the definition of odd, so you could just go straight forward. Just say, okay, n is odd, therefore, n looks like 2 times an integer plus 1, and you know what this means. So you can kind of just go straight forward. But here, I mean, what does it mean? You can't unravel the definition n is a natural number. I mean, there's nothing really more to do. Yeah, but that is a fact about all natural numbers. They're either odd or even. So this is kind of like there's two cases here. Let's consider if n is even, and then let's consider if n is odd, and prove kind of two little sub-proofs to show that no matter what integer you start with, or what natural number you start with, this will always be odd. Okay? So it makes a big difference in your proof if you start out with an even number. It's going to look different than if you start out with an odd number. Okay? So let's do those two cases. So here's my proof. So it's kind of like you have two direct proofs within one proof. Suppose n is a natural number. Okay, and I'm going to hold off until they get to the n. But your last sentence should say something like, therefore n squared plus n plus 3 is odd. But so case 1. So, and often when you do cases, you just write like case 1, and I usually indent my proof. So it's not just, I would definitely not write it in paragraph style. I would kind of start a new paragraph, and then I'm probably going to indent. So, because oftentimes you could do a proof with like 8 cases. Like, say you're dealing with two real numbers. Well, maybe they're both positive. Maybe they're both negative. Maybe one's positive, one's negative. Maybe one's 0, and maybe you might consider a different case when there's 0. Maybe one's 0 and one's not 0. So you could have a bunch of different cases. Okay. For natural numbers, and especially proving the statement about even or odd, let's just consider even integers first and then odd integers. Okay. So case 1. Suppose n is even. Okay. So I'm going to write just like a regular direct proof, assuming that n is even. I'm going to show that this is odd. Okay. We know what n is even means. That means n looks like 2 times an integer a. So then n equals 2a for some integer a. Okay? Then, think about where we're going. We're trying to show that n squared plus n plus 3 is odd. So that would mean that n squared plus n plus 3 looks like 2 times an integer plus 1. So if I start with this, if I just go straight forward, if I start with this equation, I'm going to substitute in 2a in this expression, n squared plus n plus 3. Okay? So I'll say something like this. Then n squared plus n plus 3 equals, do substitution, so equals 2a, the quantity squared, plus the quantity 2a plus 3. Okay. Keep in mind, we're trying to show that this looks like 2 times an integer plus 1. Okay. So let's multiply this out a little bit. This equals 2a, the quantity squared is, you can distribute an exponent here. So this is 4a squared plus 2a. All right, plus 3. But so how can I make this look like our definition of integer, of an odd integer?
Plus 2 plus 1.
Yeah. So I mean, clearly 3 is odd, right? But to really fit the definition, I'm going to have to break up that 3 into a 2 plus 1. So I really need a plus 1 for our definition. And you might even do that in this step. If you want to kind of save a little bit, I think it's clear enough. You don't want to do anything. You don't want to jump too far ahead where somebody reading your proof wouldn't understand. Where did that come from? Okay. Maybe somebody might say, where did that come from? But they should be able to figure it out within a few seconds. So clearly, this is 2a, the quantity squared. Here's my 2a, and then the 3 I just wrote as 2 plus 1. Okay. If you want to wait another line to do that, that's fine. All right. Then that equals. Let's say equals. Now I need to factor out 2, right? So now I have 2 times the quantity 2a squared plus a plus 1, and outside, here's my plus 1 still. So these first 3 terms are even, so I can factor out a 2. And now it does look like 2 times the integer plus 1. And let's just be, how about this? How about, so that equals 2b plus 1 for some integer b, which equals 2a squared plus a plus 1.
So we'd be at the case with that, thus that's
Yeah.
odd.
Well, yeah, or therefore, yeah, right. Therefore, n is, or sorry, n squared plus n plus 3 is odd. But this isn't, I didn't prove the whole theorem. I've only proven this is true when n is even. Okay, so if n is even, then n squared plus n plus 3 is odd. Case 2. So then, I'm going to go on the next board, but if I was going to write this on the same piece of paper, I'll write, go back out and write case 2. Suppose n is odd. Okay. Prove that case, and that's it. There's only 2 cases. I mean, n is either odd or even. So once I prove that next, the other half, then I'm done. Okay, so case 2, suppose n is odd. Then n looks like 2a plus 1 for some integer a. Does it bother you that I use the same letter a? Is it okay here?
Yeah, but you're still in the same proof.
Well, yeah, I'm in the same proof, but I'm in the same big theorem, but I'm actually in a different sub-proof, So like the a over here, it's okay if I recycle. I'm done with that arbitrary a from case 1, and so it's clear now that I'm writing a new kind of proof where n is odd, so n equals 2a plus 1 for some, But I couldn't do this in the same kind of sub-proof.
Because A is a universal variable.
Yeah, I mean a is a just stands for an arbitrary integer, and I think it's clear enough. Now, if you want to avoid any possible, you don't want anybody to mistake this a as the same a as I use over there. So you could use just different letter, but I think it would be all right to recycle his arbitrary a. So then n equals 2a plus 1 for some integer a. Okay, then we just follow the same kind of thing we did over here, right? So we have n squared plus n plus 3. Substitute in 2a plus 1. 2a plus 1 is 20 squared plus 2a plus 1 plus 3. And multiply it all out, so you get 4a squared plus 4a plus 1. You gotta do 2a plus 1 times 2a plus 1. It's a full method. Multiply that out, and you get this. Plus 2a plus 1 plus 3. Where are we going, right? We're still trying to show this is an odd number. So we still got to get it looking like 2 times an integer plus 1. So I'm going to combine some like terms here. I have a 4a, I have a 2a, so that's plus 6a. I've already got a plus 1, so let me just leave a plus 1 out and then combine maybe the 1 and the 3 here. So it's like plus 4 plus 1. Okay. Equal to, exactly. So these terms are even, so I can factor out a 2. This equals 2 times the quantity 2a squared plus 3a plus 2 plus 1 equals 2b plus 1 for some integer b, which equals 2a squared plus 3a plus 2. Therefore, n squared plus n plus 3 is odd. So I'm done with case 2.
So we end up with, so it's case 1 and case 2 are.
Yeah, you kind of refer back to your cases. You say, well, we've exhausted every case. These cases show that no matter what natural number you start with, n squared plus n plus 3 is odd. Okay, so that's why this was all kind of indented. So I go back out. If I started like my case 2 here, then kind of go back out and I'd say so it's clear that I'm not in the case anymore. That's why if I go back out, I'll say okay. So these cases show that n squared plus n plus 3 is odd for any natural number n. Box. Or QE. This is an example of proof by cases. Okay, so it's a more complicated proof because you have just more things to prove, but each individual case shouldn't be that hard, really. It's just that they're different flavor of proof because you have the cases are a little bit different flavor, so but they're similar.
I know this is obvious here, but do we ever run into a case where we have to prove that we've covered every case that's possible?
Well, that's a common mistake, right? If there's a lot of cases, if a student at first was doing a proof by cases, and say there's like 8 cases, maybe they forgot one of them, and then yeah, that's a common occurrence. Here, even or odd, that takes care of both, right? But I could think of statements like for real numbers a and b, the absolute value of a times b equals the absolute value of a times the absolute value of b. That's a true statement. Okay, so you would prove this by cases, and it all depends on whether a and b are positive or negative or equal to 0. So you can have several cases. I mean, if A is positive and B is negative, then the is negative. So then the absolute value, you would evaluate the absolute value differently than if A and B were both positive. If one of A and B is 0, then this just equals 0. And one, so you have all these different cases. I mean, so you might have case 1, A and B are both positive. Case 2, A is positive, B is negative. Case 3, A is negative, B is positive. Case 4, A and B are both negative. Case 5, A is 0 or B is 0. So I think that would get. I think I get both. I think I get all of them.
So would each case have to be independent of each other case, or could one case depend on what you get in another case?
Depend on. Well, I mean, they should be independent. I mean, you should try to partition your proof into, you're not proving the same thing for here. You don't want to reprove it again in another case. I mean, your cases should partition the whole universal set, right? Like even and odd, that partitions all of natural numbers. Every natural number is either even or odd. And so, if I give you two real numbers, they should fit into only one of those cases. Okay. Now, we're gonna run out of time, but the last thing in chapter 4 is 4.5 talks about what happens if cases are pretty much identical. Like, say I was doing this. Case 1, A is positive, and B is negative. That's maybe case 1. Case 2, A is negative, B is positive. I mean, you see how, like, really, those are pretty much the same case? I mean, basically I'm saying one is positive and one is negative. That's what's important here. It doesn't matter which one I chose. So 4.5 addresses this. When you have two cases that are pretty much identical, just, there's nothing special about the letter A and B in this proof. So oftentimes you wouldn't do that. You wouldn't go through all the same details again. So we often say, well, this case is symmetric to the previous case, so I'm not even going to do it. I'm not even going to show it. I mean, it's pretty clear, this one. If I've already proved this case, I don't really need to do this one. And oftentimes, another phrase they'll use, I'll talk about this on Wednesday, is without loss of generality. So without loss of generality, let's just assume that A is positive and B is negative. I don't even really have to worry about the other case where B is positive and A is negative. It's the same thing. They're identical proofs, essentially. Just change the letter A and B. So that's the last thing I want to do today, but we're running out of time. So if you want to go ahead and start a couple of these cases, I'll do, I was going to do one more proof, but I think for, it's not even really a proof by cases, so it's one of these without loss of generality proofs. But, so here's a couple of statements you can prove using cases. I think one of them actually can give you that hint in the book or something. Maybe like number 13 is very similar to number 14, I think. Let me look real quick. So, so number 14 does say you try cases. Okay. And then number 16, it also says try cases. Yeah. So these are both proof by cases. And it should be clear what the cases are. When you read the statements, the first one is like this. Instead of natural numbers, you're given integers. Well, it's true that every integer is either even or odd. So that's probably where you want to go. Number 16, it says, if two integers have the same parity, then their sum is even. So if two integers have the same parity, then what are the two logical cases you consider?
Both even or both odd.
They're both even or they're both odd. Okay, so it's just the proof by cases. It's usually pretty clear what your two cases are, and so your proof will look different if you're assuming they're both even, and than it would if you're assuming they're both odd. Okay.
Did you ever have a case with any case?
Sure, I guess you could. I mean, that might be a signal you need to refine your cases. Maybe you should have broken down your cases a little bit further at the beginning. But yeah, we're only going to do, like these couple of examples like this where you have two cases. I'm not going to, even this one right here, this one is kind of annoying when you're looking at like 5, 6, 7 cases, so. But, so I'll talk about 4.5 a little bit more on Wednesday. Yeah, you can keep it if you want. Yeah. I'm going to keep your Dr. Bauer said, if this is what your stutter does, then you need a new stutter, right? You've got everything except for the words on the paper, right?